take it away.
Thank you, Simon. First off, I'd like to thank the organizers for inviting me. This is, in fact, my first talk, so I'm super grateful for the organizers for trusting me. The topic of today's talk, as Simon has just said, is constant root number on integer fibers of elliptic surfaces. This stems from a research project that I did with my supervisor, Julie Desjardins, 2 summers ago during my undergrad. Julie is actually also here in the audience today, and she has been extremely grateful, extremely generous in helping me prepare for this talk. So I hope everything goes well. So here's a roadmap for today's talk. First, we will go through some background information, relevant definitions and theorems, and talk about some questions and conjectures. And then we will move on to the main object of study, which is families of elliptic curves. We define what this means and look at different types of families and give motivation on why we study the particular ones that we do. After setting the stage, we will look at a particular family. We denote this by the F family with this specific parameter that we will introduce later on. And finally, we will go over some results and look at some interesting consequences. So let's begin with the definition of an elliptic curve. So this is an algebraic curve of genus 1, and it has a specified base point and a Weierstrass equation of this form, where the coefficients are in our field K. For the characteristic not equal to 2, we can write via a change of variables the Weierstrass equation of this form, where the BI's are defined in terms of the AI's. We can also define these invariants in terms of the BI's. And we will see this come up later on. Now for characteristic not equal to 2 and 3, we may further reduce this to a Weierstrass equation of this form with 2 coefficients. And we will often denote this by capital A and capital B. And we see here that the discriminant and the J invariant can be defined in terms of the A and the B. So now on to one of the most well-known theorems, which is the Model Theorem, which states that the group of rational points is finitely generated. It is a finitely generated abelian group, and hence it has this structure here, where we have a torsion part and a free abelian part, and we denote this R by, we call this R the rank. We understand the torsion part quite well. So for example, by a result from Masser, we know that the torsion subgroup is isomorphic to one of these subgroups. The rank, however, remains quite mysterious. So one of the most famous conjectures related to this is the Burton-Swinnerton-Dyer conjecture, also known as the BSD conjecture. I'm just going to state a weak version of it, which says that if we define the analytic rank as the order of vanishing of the L function at S equals 1, where the L function is the L function associated to the elliptic curve, then the conjecture states that the analytic rank is equal to the rank. So this conjecture is widely believed to be true. And it is actually proven for the analytic rank equals 0 and 1. And this is the result of many mathematicians. Closely related to the rank is something called the root number, which is defined as the parity of the analytic rank. And so it follows from the BSD conjecture that, in fact, the root number is equal to the parity of the rank. or equivalently, the analytic rank and the rank have the same parity. So this is also known as the parity conjecture. So one question that we may ask about the rank is, how large is the rank on average? Another conjecture, famous conjecture related to this question is conjecture of Goldfeld, which states that if we consider the quadratic twists of E, all the quadratic twists of an elliptic curve, then around half of it have rank 0 and the other half have rank 1, leaving the rest having rank greater than or equal to 2. So this conjecture is also widely believed to be true. In terms of the average rank, something else we can look at is this value here, and this we define as the average rank. And here it's summing over all elliptic curves whose height, the h function here, this is the height, is less than or equal to x, and we take the limit as x goes to infinity. Now this height here is defined in terms of a and b, where recall a and b are the coefficients from the Weierstrass equation of the elliptic curve. We have a result on this average rank, and it was shown by Bhargava and Shankar that the average rank is at most 7/6. So here we have an upper bound for the average rank. So a natural question to ask is, do we have an upper bound for the rank? So this is also a very well-known question, which is how large can the rank actually get? A conjecture says that the rank can be arbitrarily large. However, this conjecture is not widely believed to be true. Some people believe it is true and some people don't. To give you an idea of the history of finding elliptic curves with high ranks, I propose that we take a step back in time, all the way from the beginning. A number of years passed by, and it was first in 1983 that we first discovered an elliptic curve of rank greater than or equal to 3. Now, shortly after that, we found one greater than or equal to 4. Then things stagnated for some years, to be more precise, 3 decades. Then in the mid-1970s, we picked things up again and we showed the existence of elliptic curves greater than or equal to 6. And since then, we've made a lot of progress, and we continue to increase this record of elliptic curves with high ranks. And we can see that all the way until 2006, when we found an elliptic curve of rank greater than or equal to 28. So it would seem like we'd expect this quest to continue. However, in 2018, the tables seem to have turned, and we, in fact, now have a heuristic that suggests that the rank is actually bounded, and in fact is bounded above by 21 for all but finitely many elliptic curves. So there is without a doubt a lot of uncertainty around this question concerning exactly how high the rank can get. But for now, I'll leave this and bring us back to the main object of the talk, which is families of elliptic curves. So we denote a family of elliptic curves by this curly E. And there are 3 equivalent definitions of a family of elliptic curves. The first one being viewing this family as one single elliptic curve, where the coefficients are polynomials. So this is an elliptic curve over Qt. The same thing as before, via a change of variables, we may write this Weierstrass equation of this form. And same as before, we can write these invariants in terms of the A and the B. The second equivalent definition of a family of elliptic curves is more like a family, because now we can view it as this collection of ETs, this collection of elliptic curves as T varies over the rationals. We call each of these ETs a fiber. In particular, when T is rational, we will call this a rational fiber. And if there's an integer, we will call this an integer fiber. Now, the last equivalent definition would be an elliptic surface. I won't go into detail in terms of this definition, but I just want to note that the term fiber here essentially comes from, is inspired by this definition of an elliptic surface. What we will focus on in this talk is essentially this definition over here. Onto more vocabulary, we say that a family of elliptic curve is isotrivial if the J invariant is constant for all rational T, or else we say that it is not isotrivial. And we will come back to these two terms later on. In terms of reduction mod P, usually we categorize the reduction in terms of whether it is good reduction or bad reduction, where bad reduction is multiplicative or additive. Now, because now our elliptic curve is over QT, we can instead look at reduction mod P of T, where P of T is an irreducible polynomial, and the definitions here remain the same. For the purposes of our study, however, we want a finer classification of the reduction types, and here we introduce what is called the Kodaira type. And this classification depends on the evaluation of the discriminant and of the coefficients at the polynomial P of T. And we can see that the Kodaira type here is much finer than what we usually have as the good, multiplicative, and the additive. We see that here the Kodaira type is represented by these Roman numerals over here, and we'll see them as well later on when we talk about the root number. So introducing the star of the show, which is the root number, we use this as a way to study the rank. Again, here's the definition of a root number that we briefly talked about before. It is the parity of the analytic rank. And again, by the BSD conjecture, we have that this is actually equal to the parity of the rank. I just want to make a note here that this may seem obvious, but if the root number is -1, then that means the rank must be odd, and hence it is non-zero, which is particularly interesting to us. Now, what we ultimately want to do at the end of the day is to compute the root number, which means we need an alternate definition for us to be able to compute the root number easily, because from this definition, we can't really, it's very difficult to compute it this way. So now we introduce an alternate definition of the root number, an alternate but equivalent definition. And this is the product of these WPs, which we call the local root numbers. Each of these local root numbers is defined in terms of the epsilon factors of the Veil-Deligne representations of QP. And they are each ±1, and they're in fact equal to 1, except for finitely many P. More details can be found in these two references. Now, the reason that we want to use this definition is because we have this particularly nice formula for the WPs. in terms of these Legendre symbols, and these depend on the codaritypes mentioned earlier. And this is a very nice result from Rolik 93. Note that this is for primes greater than or equal to 5. Now for primes equals 2 and 3, we refer to tables in Halberstadt and Rizzo. So now that we've introduced both the root number and families of elliptic curves, let's now look at how the root number varies, how it behaves in these families. We begin by introducing these two sets. This is taking notation from Desjardins, where we define W plus to be the fibers whose root number is +1, and W minus to be the fibers whose root number is -1. And we want to look at the cardinality of these two sets in a particular family. So if the family is isotrivial, recall that isotrivial means the J invariant is constant. In this case, two things can happen. Either that these sets are both infinite, which means that the root number is not constant for all rational fibers, or that one of them is empty, which means the root number is constant. So we have an example here. If we take a look at this family, we see that this family is isotrivial because the J invariant is the constant 1728. This family, in fact, has a constant root number of 1. Now, if the family is non-isotrivial, then under certain conjectures, so I will briefly state what these conjectures are. So the conjectures here that we are referring to are these two conjectures, the what's known as the Chowla conjecture and the square free conjecture. So essentially, this has to do with if we're given a polynomial with integer coefficients that's primitive and square free, then Chowla's conjecture gives us an estimate on the number of values ft such that the number of prime factors has some certain parity. So this conjecture has to do with the Liouville function. The square free conjecture, on the other hand, gives an estimate on the number of elements T in this AT, and AT I define it as this bounded arithmetic progression. So it's a number of elements such that FT is square free. So now you may ask, so what does this have to do with what we're talking about? Essentially, we want to apply these conjectures to these two polynomials, respectively, Chowla's conjectures to this product of places of multiplicative reduction, and the square free conjecture to the product of the places of bad reduction. And I just want to make a note that Chowla's conjecture actually holds for polynomials of degree 1, and square free holds for degree at most 3. So I haven't stated the result yet. The result is if we assume these conjectures for these two polynomials respectively, then a result by Desjardins says that W plus and W minus are infinite. And then being infinite means that the root number is not constant. Also, just want to make a quick note that the versions of Chowla's and square free conjectures that we're talking about here is one variable, whereas in the proof of Desjardins, she uses a 2 variable version. Even though these two sets are infinite, if we look at these two sets instead, these are not necessarily both infinite. So note that here I'm defining two new sets. These are W plus and W minus, same as before, except now that we have T in the integers instead of the rationals. So here we're looking at integer fibers instead of rational fibers. Even though the above result says that the rational fibers do not have constant root number, that doesn't necessarily mean that the integer fibers don't have constant root number. And a motivating example for this is the famous Washington's example, which is defined by this Weierstrass equation over here. Research showed that for this family, all integer fibers have the constant root number -1. And in fact, one can check numerically that the rank is 1 for t less than 1,000. Also here, I just want to make a side note that if we find that the root number is 1 instead of -1, then by the parity conjecture, the rank is even, but we can't really make any more conclusions. We can't say that it's non-zero or it's 2. So here I'm going to state our goal of this project is essentially to find more examples like Washington's. We want to come up with more families whose integer fibers have constant root number. Okay, so up until now, we've sort of shifted our focus on first non-isotrivial families, and secondly on integer fibers. Now we continue to narrow our focus to families with low degree coefficients. And by that, I mean a family where these coefficients have degree less than or equal to 2. The reason we want to do this is because we have this very nice result from Benton, David, and Delaney, who showed that there are essentially 6 different families that are non-isotrivial and of low degree. And here you may notice they have no multiplicative reduction at finite places. The reason why we have this criterion is because if we do have a finite place of multiplicative reduction, then Helfgott showed that the average root number over the integers is actually 0. And what does that mean? Well, the root number can only be 1 or -1. So if the average root number is 0, that means the root number is not constant over the integer fibers. So this result sort of helps us eliminate the case where the family has multiplicative reduction at a finite place. That's why we look at families with no multiplicative reduction at finite places. So these are the 6 different families. In blue here, I have the places of bad reduction. And in peach here, I have the cadareotypes of the bad places. So from these 6 families, what I claim now is that the only families or the only cases that even have a chance of having subfamilies with constant root numbers on integer fibers are the F family and the L family with this requirement on S. So notice S, we have this parameter S over here. So in F and L here. And why is that? So to see why this claim is true, or at least true, assuming some conjectures, first we want to define the notion of what it means for a bad place to be what we call insipid. So we say that a finite bad place is insipid if the polynomial satisfies one of these 3. So either it has this cadareotype or one of these cadareotypes, and it is of this form, and so on. So what are we going to do with this definition? Well, a theorem by Desjardins says that if we have a family of elliptic curves and this family has a bad place that is not insipid, then assuming the Chala and the square free conjectures, we have that the root number is not constant on integer fibers. So let's try applying that to our 6 families. So say we look at G, right? So if we look at this place of bad reduction, T minus 1, is cadareotype 2. Now, is this insipid? Well, we look here, it has cadareotype 2, but t minus 1 is not of this particular form, which means that this bad place here is not insipid, and hence it satisfies the assumption of this theorem, which means that the family G does not have constant root numbers on integer fibers. And we can do essentially do the same for all of these four, which leaves us with F and L. So what happens for these two families? If we look at the F family, right here, t squared minus s with cadaretype 2, we see that by this definition, cadaretype 2, t squared minus s, it is of this form, precisely when s is of this form. So when s is equal to 3 times an integer squared. So that means for these two families, well, by P of t, technically, one is this one is this one. But for both cases, they are insipid if and only if S is of this form. Notice that they don't have any other bad places, which means when P is of this form, then we cannot apply this theorem because there are no places of that are not insipid. That doesn't necessarily tell us that the root number is constant on integer fibers. It just tells us that we cannot apply this theorem, and hence there's a chance that we can find a subfamily with constant root numbers on integer fibers. So essentially what we did here is to eliminate these four families. Now we're left with the families F and L. And next up, I'm gonna talk about the family F. So this family has this Weierstrass equation. By a change of variables, we can write it like this and compute the discriminant. We see that the polynomial t minus s divides both coefficients as well as the discriminant to a power of 2. Checking the table of cadaretypes, we conclude that this is cadaretype 2. Now what we want to do is compute the root numbers, and recall we had this formula for the root number. We want to be able to conclude that the left-hand side is constant for all t in Z. But how do we use the right-hand side to do that, right? So what we really want is something like this. We really want that we want that the left-hand side is constant for all t, if and only if every factor on the right-hand side is also constant for all t, for every prime. So this is sort of like a local global principle. However, with the equation written like this, this actually doesn't hold, unfortunately. So even if we are able to compute the WPs, and even we're able to conclude that, oh, the WPs, each of them is constant for every t, we are not able to conclude that the left-hand side is also constant. So we need to do something about this. What we do is essentially we need to rewrite this. We need to rewrite this, the right-hand side. We need to rewrite it so that each local contribution, so each WP behaves independently. And this is done by introducing Jacobi symbols and the Liouville function, and this is much more detail is given in Helfgott and Desjardins. What this process of sort of rectification gives us is something we call the modified local root number. So now we're working with WP with a star here. And as you can see, what by adding these extra symbols, now we have sort of like a corrective function in front of the local root numbers. And it is a theorem from Desjardins that the left-hand side, so if we compare this versus this, it's the left-hand side remains the same. It's still the root number, and the right-hand side, now we can write it as a product of these modified local root numbers. So now what's good about this is that now this local global principle that we wanted from before, if we replace that with a WP star, then this actually holds. So what that means is now we can look at the root numbers independently, each local root number independently, compute them, and then summarize, conclude for the global root number here. And here I just make a note that we can compute the modified local root number from results from Chinis and then Delaunay, and the modified local root number essentially it depends on the evaluation at P of S of the various T's of P of T and so on. So now I just want to restate our goal again, recall the first time we stated it was to find more examples like Washington's. So now to narrow it down, what we really want to do now is to find conditions on S so that our family has constant root numbers and integer fibers. Note the stress on integer fibers and not rational fibers. Before I state the result, I want to look at some examples. So let's take S equals -3 for a second. Then one can compute that if we take this fiber, so namely this is T equals 2. This is the F family, by the way, we're working with the F family now. So if we take T equals 2 and we take T equals 6, then one can compute that the modified local root number at P equals 2, it is 1 for T equals 2 and it is -1 for T equals 6. So what does that mean? Well, from what we concluded above here, from the local global principle, well, if it's not constant for P equals 2, then it's not constant for the global root number either. That means that S equals -3 does not work. So S equals -3 does not give us a family with constant root numbers on integer fibers. Okay, so why don't we try something else? So let's try S equals -3 times 2 squared. So again, we can do the same thing. We can now say like T equals 4 and T equals 8. We see again it has opposing root numbers, hence the family does not have constant root numbers. Again, we do the same thing with S equals -3 squared, S equals -3 times 4 squared, and so on. We can keep on finding these fibers with opposing local modified local root numbers at P equals 2. Right, so what is happening? This leads us to our first theorem, which says that if we recall the set, this is the set of integer fibers such that the root numbers is plus or minus ones. This is two sets, W plus and W minus. Then our result says, then both of these sets are infinite. Another way to interpret this is there does not exist any S such that this family has constant root number for all integer fibers. So it seems like we are in deep trouble and that we've hit a dead end, because if you recall just a moment ago, what was our goal? Our goal was to find conditions on S so that the family has constant root numbers on integer fibers, but our result is telling us that there does not exist any such S. So it seems like we have failed, but recall Washington's example, right? That was our motivating example, and that was a family that had constant root numbers for integer fibers. Now you may think, okay, maybe what does that have to do with the F family? Maybe it's not even a part of the F family. What we proved is a result for the F family. The Washington example, who knows what family that's in. However, one can show that the Washington family is in fact isomorphic to a subfamily of the F family under when S, A, and B takes these values. So it's a subfamily of the F family, but it has constant root numbers on integer fibers. But we just showed that F family doesn't have constant root numbers on integer fibers. So what is going on here? Well, in fact, if the root number is constant, if we take a family and we show that the root number is not constant, sorry, if it's not constant for all T in Z, then in fact, that does not imply that the root number is not constant in subfamilies. You know, when we say subfamilies, we mean when we run T through a subset, so for an arithmetic progression of Z instead of all of the integers. So that means we are back in business, and now we can consider, instead of considering varying T over all the integers, we can now vary T over these arithmetic progressions, subsets of the integers. And now that brings me to my our second result, which gives conditions on S, A, and B, with S still being of this form, such that this subfamily here, so we're still in F, the subfamily of F has constant root numbers as U. So now instead of T, we have this U here, as U varies through the integers. And we show that it has constant root numbers if and only if the following three conditions hold. So the first one has to do with the valuations of A and B and S at primes greater than or equal to 5 subprimes, the P divides S. The second condition has to do with basically the same thing, except now P equals 3 because the computations is slightly different for P equals 3. And finally, the third condition is for P equals 2. Now, while I was preparing for this slide, I wasn't sure whether I should just end it here or actually write out the conditions for 2, but I thought the audience probably deserves the full glory of P equals 2. So here it is. These are the conditions. Notice it just needs to follow, satisfy one of the following. But it is these conditions for P equals 2. And it's not too bad, actually. And this is all the conditions that we need on S, A, and B in order for this subfamily here to have constant root numbers on integer fibers. Okay, so that was a lot. Let me summarize what we actually did in words. So basically, given a non-isotrivial family of elliptic curves where the degree of each coefficient is less than or equal to 2, then if we assume childless conjectures and the square-free conjectures, what we showed is that these sets, these two sets, W plus and W minus, they are both infinite. Recall that if they're both infinite, that means the root number is not constant. So they are both infinite unless our family is either a subfamily of the F family with the conditions that we just saw, or is a subfamily of the L family, which also has a bunch of conditions which I didn't list here, but it's quite similar to the F family, but a lot longer. So before ending, I'd like to talk about a very interesting consequence of this. Here, I'll first define what the generic rank means. So recall that we can view this curly E, this family of elliptic curves, as one single elliptic curve over QT. And hence we can talk about the rank of that one single elliptic curve, and that's what we call the generic rank, as opposed to the rank of each individual fiber. So a theorem from Silverman, this is Silverman's specialization theorem, and this says that the generic rank is at most the rank of the individual fibers for all but finitely many fibers. Another theorem by Ben, David, and Delaunay says that if we look at the F family, then the generic rank of the F family is 1 if S is of this form and otherwise 0. So what these two theorems give us is that when S is of this form, then the rank of the fibers is at least 1. So this is applying the Silverman theorem to this result over here. Now, why is this interesting? Well, if we go back to our F family, and if we're able to find a subfamily here, all of whose integer fibers have root number 1, then what does that tell us? Well, under the parity conjecture, we call the root number is the parity of the rank. The root number is being 1 means that the rank must be even. But by this result, we see that the rank is greater than or equal to 1, which means it being even must be non-zero, and hence this means that every non-singular integer fiber has rank 2 or more. Now from theorem 2, we can actually compute, we call theorem 2 is the one with the all the conditions. From that theorem, we can compute conditions on A and B under which this family has constant root number of 1. And here's just one particular example. Say we take S equals minus 12 times 5 to the 4, and A and B are of this form. Writing this out in terms of its Weierstrass equation, we see that this family looks like this. Our theorem tells us that for this particular family of elliptic curves, every integer fiber, that means for every U here, if we sub in an integer, that means the rank is 2 or more in this family for all integer fibers. Oops. So to give a concluding summary, I like to take us back to the very beginning when we first encountered rank and its obscurities and its mysteries. We defined the root number as a way of studying the rank. And then we looked at the behavior of root number in families of elliptic curves. Then motivated by Washington's example, we shifted our focus to non-isotrivial families and their integer fibers. From here, we narrowed our focus even more to families with low degree coefficients and no multiplicative reduction at finite places. And we did this because there's a very nice result where we know that there are exactly essentially six families that satisfy this. From the 6 families, we were able to eliminate 4 of them and essentially show that these two families with this particular S, we show that these two families are candidates for having subfamilies with constant root numbers and integer fibers. And then our final result gives conditions on S, A, and B such that this is true, such that this subfamily has constant root numbers for all integer fibers. From this result, we have at our disposal many, many examples of families with constant root numbers. Again, integer fibers. In particular, we are able to generate examples of families where all of its integer fibers have rank greater than or equal to 2, which is particularly interesting because this is a relatively rare occurrence, given that your usual run-of-the-mill elliptic curve has, or at least conjectured to have rank 0 or 1. So having an entire family, all of whose integer fibers have rank at least 2 is quite interesting. And that just ties back to our original quest to find out more about the rank and to bring some concreteness into the sea of abstraction. And that brings me to the end of this talk. Thank you for listening.
Thank you very much. So we'll invite everyone to unmute and thank our speaker.